Climate change is one of the most important challenges of our time. It's estimated that the Earth temperature will increase around 1.5 degrees Celsius per decade. That means that 100 years from now, our children and grandchildren will live in a planet when the temperature is higher by 15 degrees Celsius, which is scary, right? Therefore, you may be thinking, how can we stop it? One of the alternative solutions involves an energy shift from fossil fuels to renewable sources. Biomass is an alternative energy source that represents 5% of the primary energy generation in the US and is expected to grow. Even though 5% doesn't seem like a lot, biomass has the advantage that it's the only alternative energy source that can produce fuels that will work in the cars we drive today. Generally speaking, biomass is any organic material or waste, rich in hydrogen, carbon, and oxygen. Biomass can be converted to liquid fuels by chemical transformation. However, its conversion is not straightforward. One of the most critical steps for this process is the oxygen removal to make these molecules to behave more like gasoline. The presence of oxygen on liquid fuels can cause many issues with the storage, transportation, and industrial applicability. Now, how can we remove the oxygen from biomass-derived compounds? Well, the oxygenation process, which involves the removal of oxygen of the molecules, can be catalyzed with metal oxides. You may be thinking, what is a catalyst? Catalysts are the materials that speed up the chemical reactions by reducing the energy barrier to go from the reactants to the products. In my research, I have focused on studying different metal oxides as a catalyst that are very selected for oxygen removal. I have found that the molybdenum oxide is a wonderful catalyst for the oxygenation of biomass. Recently, I found that the incorporation of small platinum loadings greatly improved the catalyst performance. As you can see in the graph behind me, the incorporation of platinum also drops the energy barrier by 50%, favoring the generation of fuels like molecules. I have also designed a kinetic model that will not only help us to understand these chemical transformations at a molecular level, but also determine the impact of different parameters on the reaction conditions on performance. Finally, I do believe that this knowledge can be applied industrially, and the refineries of the future can be like the ones we have today, but with a sustainable and environmentally friendly feedstock instead of fossil-based source. Thank you.